So mark your own. Do my usual. They want the, oh, nice try. It says an airplane turns a horizontal circle in 2 minutes. I'm not going to fall for that. That's 120 seconds. They want the radius of the circle. They've given me the speed. So to do this, you're going to need to use circular speed. This equation is not on your formula sheet. You'll have to either memorize it or, better yet, memorize how to derive it. It is distance, which in a circle once around is 2 pi r, I'm pretty sure, over time, which in a circle we call the period. They want the radius of the circle, so the radius is going to be the speed times the time divided by 2 pi. It's going to be the speed, 170, times the time divided by 2 pi. Come on, pen. Come on, calculator. It's going to be 170 times 120 divided by 2 pi. And you get a radius of 3.25 times 10 to the third meters. Radius is about 3¼ kilometers, which at first I went, that seems, no, you know what, that seems about right. A plane taking 2 whole minutes to do a circle, traveling 170 meters. Yeah, that's about right. Gut instinct, sure, that seems good. What's the acceleration? Okay. Well, I can either use the, oh, you know what? I think I'm going to use the v squared over r. I could use the 4 pi squared r over t squared. I know the period and the speed. Now, no matter what, I'm having to use the radius from part A. If you didn't get the radius from part A, I hope you were clever enough to write down or make up a radius for part B and say, look, I can crunch the numbers. And if you did do that, you will get 2 out of 2, assuming you've done your work right. My speed is apparently 170 squared divided by the radius. So it's 170 squared divided by this. 8.9 is the acceleration. And units meters per second squared. By the way, in terms of part marks, I'd probably give you 1 mark if I saw that, half mark for that, half mark for the answer. Here I'd give you 1 mark if I saw that, half mark for that, half mark for the answer. So if you made up a radius and you went 170 squared divided by whatever your radius was and hit equals, you can give yourself full marks. Number 2. What's centripetal force? Okay, they want a force. Centripetal force is mass times acceleration, because force is always mass times acceleration. It's going to be, oh, they gave me a frequency. They told me that the frequency was 5 hertz. However, if I know the frequency, I automatically know the period, because period is 1 over the frequency. They're reciprocals of each other, which I think is on your formula sheet, isn't it? Yeah, it is. So it turns out the period is going to be 1/5, or if I want to decimalize it, it's going to be 0.2 seconds. If it goes around 5 times every second, it takes 0.2 seconds to go around once, trust me. So they did give me the period. I'm going to use the m 4 pi squared r over t squared. I'm going to use the m 12 4 pi squared 6 over 0.2 squared. 12 times 4 times pi squared times 6 divided by 0.2 squared. And I get, holy smoke, 71,000 newtons. In terms of part marks, I'd probably give you a half mark if you found the period correctly. I'd probably give you 1 mark if I saw that, a half mark for that, and a half mark for the answer. Now, I was looking at this, 71,000 newtons, that seems really high. Wait. What's the mass in this question? You know what? Remember that lead weight, that ball that I had? That was about 12 kilograms. What's the radius in this question? 6. So 6 meters is about from me to Zach. So imagine a rope from me to Zach with that huge ball on the end of it and me spinning it around and around. Oh, and how long is it taking to go around once? That means it's going around once about, no, way faster than that. It's going around once about, I don't think I could do that as a human. You'd need a machine to do that. In fact, I think if you walked into that, that would kill you. You know what? That forces, I'm okay with that. I thought it was really, really big, and then I went, nah, that works. I'll give you probably 1.5. I'll give you 2. Well, no, you know what? Yeah, 2, because I said 1 mark for the equation up there. So you found the circular acceleration, not a force. Did you call it meters per second, or did you call it squared, or did you call it units, newtons? Not a force. Oh, in number 4, all they want is the acceleration, which means my units are going to be meters per second squared. I'm not going to multiply by a mass. Which one am I going to use here? They gave me the speed, so it's going to be v squared over r. It's going to be 5 squared over, nice try. It says centimeters. I'm going to change that to meters. Thought they'd get me there. I'm not going to fall for that. And I think, do you get exactly 100? Yeah. Technically, you should put a dot there to make it 3 sig figs. I'm not going to freak out. What would my units be? Cole? Darn right. I'd probably give you 1 mark for that, half mark for the numbers, half mark for the answer, and then I'd probably say turn the page. A Ferris wheel. Oh boy. They want the force at the top that the bench exerts. They want the normal force. I quickly did a little free body diagram. I said, there's my person. We're at the top. I have normal force up. Why did I draw gravity so much clearly the winner? Because the net force has to be towards the center. So my equation here is going to be gravity minus normal force equals mass times acceleration. I think that's going to give me a normal force equaling to gravity minus mass times acceleration. I think the normal force is going to be equal to mg minus m period or velocity period 4 pi squared r over t squared. It's going to be mass times 9.8 minus mass times 4 times pi squared times the radius, 9, divided by the period squared. And you get 626 newtons. I'd give you 1 mark for that and 1 mark for the answer. B, now we're at the bottom. Okay, at the bottom, gravity down, but my net force has to be inwards. Normal force has to be winning. Has to be. How do I know? Because when you're moving in a circle, the net force is towards the center. That's going to be normal force minus gravity equals m4 pi squared r over t squared. Mass times acceleration. That's going to give me a normal force of gravity plus m4 pi squared r over t squared. In fact, Brett, I think it's exactly the same thing on my calculator, except instead of a minus sign right here, you know what I can put instead? You get 648. Mr. Dweck, how come those answers are so close to each other? 626, 648. What's the period of this Ferris wheel? What did I say in the question? This thing's barely moving. It takes 45 seconds to go around. I mean, that's pretty slow. I was making up numbers, and here I think I made up bad numbers. Everything else was okay, but I think next time I go over a Ferris wheel, I'll sit there with my stopwatch, nerd that I am. I'll time myself to go around once. I think they're closer to 10 seconds or so.
I thought it was around 45.
On a Ferris wheel?
Well, I haven't been on a Ferris wheel in a while.
It depends on which ones you... I know the Playland one is less than 45. The only other big Ferris wheel that I've been on is the one at California Adventure Park, Disney World, where they have the big Mickey Mouse one. I've been on that one, but that one, they're always loading people on and off. You only actually go around like about 5 times before they stopped, and so I've never remembered to time that one. I can do that when I'm standing in line. Since I'm going to Disneyland in spring break. Fresh data, yes. What, you thought I was going for Mickey? No, I'm going for amusement park ride data, absolutely.
Yeah.
For me?
I can't do like the simplest things. I just not thinking like about physics class now.
Well played, I say. If I do my job, then it's a physics universe, man. Speaking of, let's go to outer space. Suppose we're building a circular space station, and we're going to use centripetal force. Okay, so we looked at this. We said what we're talking about here is the only force acting on the person, the normal force. What we're really saying is normal force equals circular force. And since they're asking for the period, I'm pretty sure this is going to be mass times acceleration. And as you've heard me say many, many times, I don't know the normal force. Except this time I can't say, oh, but look, I know another force the same size as the normal force, because looking at my diagram, I only got the normal force. But in the word problem, they told me they want this to be 75% of gravity. In fact, Zach, you may have been clever enough to just actually skip this line. You may have actually just said, hey, really what we're saying, if we want it to be 75% of the Earth's gravitational field, and gravitational field, you taught us last day, Mr. Duick, was another expression for the acceleration due to gravity, you might have just said, Duick, the equation we're going to use is 75% of 9.8 equals 4 pi squared r over t squared, because this cool is an acceleration equals an acceleration, so I don't need a mass in front. They want the period. That's going to be 4 pi squared r over 0.75 times 9.8 square rooted. That's going to be 4 pi squared, what was the radius, 160? All divided by 0.75 times 9.8. 4 pi squared times 160, all divided by 0.75 times 9.8. That's way, square root, Mr. Duick. And you get a period of a little over 29.3 seconds. In terms of part marks for this one, I'd probably give you a half mark for that, 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 and 1 mark for the answer. Can you give yourself a lovely clear score out of 16 and each of you give yourself 1 bonus mark for free, please?
I don't know why. What was the equation on that last one? That G, M1, M2, E2.
Sensing people haven't done all the homework. Number 9, a 1,000 kilogram rock has a weight of 1,200 newtons. The radius, find the gravitational field. All right, who asked me number 9? Brett did? What did they tell you? They told you the weight. Remember, weight is another word for Fg, and that equals mg. And in A, if they want you to find the gravitational field is going to be the force divided by the mass. It's going to be 1,200 divided by 1,000. This particular asteroid has a gravitational field strength not of 9.8, of 1.2 meters per second squared, which tells me it's way, 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 way smaller than the Earth. You okay with that so far? Yeah. Okay. They gave me the mass. They gave me the weight. Remember, weight is code, is physics talk for mg. If they give me m and they give me mg total, I can find g. When we're talking about gravitational field strength, what we're talking about is little g, not big G, that Newton's gravitational constant of 6.67. That's the conversion factor we need to end up in newtons. Little g is what we call 9.8 here on Earth. Every planet has their own little g. Every asteroid has their own little g. And it's only 9.8 on the Earth's surface. Later on today, we'll be asking, hey, what's the gravitational field strength out there somewhere? It gets smaller as you get further away. What does B want us to find? Okay. We also said there was another way to calculate little g that way. But we also said this. Gravity equals gravity.
That's pretty obvious, Mr. Duke.
No, I'm not done yet. Gravity equals universal gravity. We did this last day too. What do you see canceling? And in fact, what I'm really saying, this is not on your formula sheet. I've just showed you how to derive it. There is how you can calculate gravitational field strength. Or in this case, since I know the gravitational field strength, I should be able to find the mass of the asteroid. Let's get the m by itself. The r squared is going to move up, yes? Big G is going to move down, yes? We're going to get this. Where little g is from part A, 1.2. They told me the radius of the asteroid, didn't they? 3,500 meters. 3,500 squared divided by 6.67 times 10 to the negative 11. Or, Brett, if I knew the mass of the asteroid, I could calculate its radius if I knew its gravitational field strength. Or, if I know its mass and its radius, this is how we found G on the moon before we went there. This is how we found G on Mars before we went there. Or whatever the numbers are, crunch them, but that should give you the answer. Is that okay? Yeah. Let's go cosmic. Let's go into orbit. The physics of satellites, of space shuttles, of the International Space Station, and of planets. Example 1 says, draw a force diagram for the mass little m in orbit. So what are the forces acting on mass little m? And I am going to say, get the obvious one, but just be a little bit careful. What is the obvious one? Gravity. Which way? Zach? Can and you know what? What shape do you see? So instead of saying towards the big M, could you say it another way? Toward, huh? Towards the center. What path is little m, the satellite, the moon, whatever, tracing out? A circle. What force is pulling it in a circle? Gravity. You know what that means? This is going to be the equation that we're going to flog to death today. This is going to be my starting point, this equation here. Gravity is what's pulling it in a circle. This is going to be our ongoing theme. This is going to be our starting point. If we're in orbit, I know that. An orbit, I wrote, is circular motion with gravity as the inwards force. Example 2. A 10,000 kilogram satellite is orbiting 20,000 kilometers above the Earth's surface. Can you underline the 20,000 kilometers above the Earth's surface? That's going to be important. Because what they've just given us is that 20,000 kilometers above the Earth's surface. Brett, what I need to use is that distance there, because that's the orbital radius. How can I figure out that distance there? I'm going to take that 20,000 and I'm going to add something to it. Radius of the Earth, okay? So the first thing I'm going to write here is our orb is our Earth plus altitude. Sometimes, Courtney, they'll give you the orbital radius in the question. Great, then you're good. Just use it. But if they say above the Earth's surface or at a height of or at an altitude of, add the radius of whatever planet we're dealing with. Usually the Earth, but sometimes we'll do the moon just to be different, or Mars just to be different, or, you know, let's use the universe. It's our playground after all. So in this situation here, 6.38 times 10 to the 6th plus, and it's 20,000 kilometers. 20,000 kilometers is how many meters? Take that 20,000 and multiply it by what? 1,000. 2 times 10 to the what meters? How many zeros do you have right now in the 20,000? How many, count carefully, how many zeros do you have right now? 4. When you times by 1,000, how many more zeros are you going to add? 3. So are you saying it's that? Yes. What is 6.38 times 10 to the 6th plus 2 times 10 to the 7th, please? Come on, got calculator. Wait, you're going to need your calculators out today and your formula data sheets out today, big time. So get them out. We're going to be, in fact, we're going to be cube rooting today, so you're also going to have to find where your cube root button is later on. You get 2.638 times 10 to the 7th? And I'll keep my extra sig figs. This is not my final answer. This is what I need to do before I can even start. I need to say, hey, Sean, I need a radius. Alejandro, what's part A asking me to find? I'm going to tell you what it is right now. What path is this satellite tracing out? What's pulling it in a circle? What's pulling it in a circle? Here's your force equation, Fg equals Fc. B says find the orbital speeds. We're going to have to rewrite these equations. Gravity isn't going to change. Gravity is always going to be big G, big M, little m over r squared. That's Newton's universal law of gravity. Fc, well, cool, that's going to change depending on what they give you or what they ask for. Now, it's a force, so what am I going to start out with? Always a little mass. Which acceleration? What do they want me to find in part B? I think I'm going to use v squared over r. If they asked for or gave me the period, I'd use the 4 pi squared r over t squared. What do you notice? What cancels? Turns out the height that you need to orbit at doesn't depend on the mass of what's orbiting, which is a good thing. That's what allowed us to put small satellites into a big space shuttle, have the space shuttle get them to their orbital height. The space shuttle could also orbit there, have the space shuttle carefully lift it out of their cargo doors, have the space shuttle duck down below, and now we're in orbit with this satellite. Otherwise, we'd have to somehow get everything there with rockets and stuff. Ooh, I noticed one more thing. Do you see it? One of the r's cancels, because if I take that r squared and I move it to the top over on the right-hand side, I'll have 2 r's on the top, 1 r on the bottom. One of my r's cancels. And I end up with v squared equals big G, big M over r. How would I get rid of a squared? V is going to be the square root of big G, big M over r. Which is going to be the square root of 6.67 times 10 to the negative 11. That's Newton's universal gravitational constant, not 9.8. That's the acceleration due to gravity here on Earth, completely different. Mass, big mass. Oh, Earth. What is the Earth? 5.98. I can never remember the times 10 to the 26th? I think it's 24th, isn't it? It's all on your data sheet. This is where you're going to be using it. All divided by the radius, which we said was 2.638 times 10 to the 7th. This is a time for all of you to practice with your calculators. What is the orbital speed? You get 38888. 3,900 meters per second. Don't forget the square root. Okay. Okay. So I wrote, note, orbital speed, thankfully, is independent of the mass of the orbiting object. That means to put a satellite in orbit, we don't care how big it is once we get it there. Now, the expensive part is getting it there. It is about $10,000 per pound to put something in orbit. And there's a reason why only countries or corporations that are the size of countries have satellites. There's a reason why we don't, as a science project, say, let's build our own satellite for Pitt Meadow Secondary. We could, the satellite part we could build no problem. Be expensive. We could put a cheap, crappy one up there for a couple of grand that would send a radio signal or something that we could know it was up there. Getting it up there, that'd be the problem. That's the expensive part. The energy costs, later on we'll look at the energy costs, and in those, the mass never cancels. But once you're up there, so that's why we build, for example, the space station in parts, in chunks. Bring it up with small pieces, small chunks at a time, in modules, and it's gradually getting bigger and bigger and bigger. So here is our first equation. Don't memorize it. We'll write it in the box here, orbital speed. Don't memorize it. You know what you're going to memorize, Sebastian? If you're in orbit, that right there in the box. If you're in orbit, gravity is what's pulling you in a circle. Because there's going to be about 8 different variations of these equations that can pop out. You can memorize every one of them if you really want to. Nah, start with this, and then I've taught you how to cross-multiply. And in fact, it's this equation, which is why I gave you that whole things move diagonally, cross-multiply shortcut. Next page. Example 3 says, fill in the proof below to show that when an object is in orbit, its inwards acceleration is the same as its gravitational field at that distance. Now, Brett, you may recall a few minutes ago we said that gravitational field strength was big G, big M over R squared. We said Fg equals Fg, the masses canceled, and we ended up with little g equaling big G, big M over R squared. So let's see if we can prove that if you're in orbit, that's what's pulling you around in a circle in terms of your acceleration. Not in terms of your force. That's your acceleration. I wrote down here A equals, V squared over R. And then I wrote substitute V equals blank orbit speed. Well, Zach, we just got an expression. What was orbit speed in this box? Read it to me. Look up.
The orbit equals
Yep.
big G big M over R
Square rooted. Now, you know what, though? I noticed that in my acceleration equation, there isn't a V. What's actually sitting there, Zach? You know what? Let's substitute V squared, because, Zach, call me silly. Isn't V squared equal to big G, big M over R? I have it sitting right here. Let's write this down. V squared is big G, big M over R. And if I take this, and Emily, I replace it right there. On the top, I'll get a big G, big M. Yes? There's already an R on the bottom, and what I'm substituting in gives you an extra R on the bottom. You'll end up with big G, big M, all over RR, or what's a nicer way to write RR? And lo and behold, we just proved that the gravitational field strength up there, if you're in orbit, Rob, is the same as what you feel in free fall. This has a profound, profound consequence. This means that astronauts are all in free fall. No, Mr. Dewick, they're floating. No, they're not. They're falling. I'm telling you, Mr. Dewick, they're floating. Patience. Here's what Sir Isaac Newton imagined, and this is one more reason we have so much respect for Sir Isaac Newton, the fact that he was able to visualize orbits at a time when people hadn't even sent hot air balloons into the stratosphere, let alone into outer space. He said, I'd like you to imagine a giant mountain, like in my picture A. And imagine we had a really, really strong pitcher, the strongest baseball pitcher on the planet, and he threw his baseball. And the baseball went like this, and landed there. Okay, now we do some steroids. Pitcher gets stronger and stronger. Now he throws, oi! And can you see he could actually end up with the baseball landing out of his viewpoint because it would follow part of the curvature of the Earth? Alejandro, now let's really do some steroids. It's possible the baseball pitcher could throw the baseball at just the right speed, oi! So that it's falling, but it's falling at exactly the same curvature of the Earth. It is falling down, but he put just the right sideways circular velocity on it that even though it's falling, it's never getting any closer. We call that an orbit. That's what an orbit is. Everything in orbit, nothing in orbit is floating up there standing still. Everything in orbit has just the right sideways velocity, and we'll teach you how to that speed right there, how you calculate it, so that it falls at exactly the curvature of the Earth, so that it's falling but never getting any closer. So the astronauts are all in free fall. In fact, when I jumped out of an airplane, have I mentioned lately that I jumped out of an airplane? I felt exactly what the astronauts felt, except I felt air on my face and I could hear wind rushing by my ears because the room that I was in wasn't in free fall with me. The air was not in free fall with me. But if you had put me in an enclosed building and dropped me so that the air was in free fall along with me, I would feel weightless, just like the astronauts do. We call it apparent weightlessness. So this means that things in orbit are always falling towards the Earth, even if they never get there. It explains why astronauts seem to float around in the space shuttle or in the space station. Both passengers and the ship are in free fall. They're falling at the same rate, so the ship can't exert a normal force on the passengers. And hopefully I've gone on enough of a rant the past few days that you've realized that what you guys think of as gravity is not, it's the normal force pushing up against you. And if we remove that, you feel weightless. In fact, we call that apparent weightlessness. That's when the normal force is 0. True weightlessness is when there's no gravity. That only happens if we plunk you on the edge of the universe so that you're infinitely away from any planets. We can't do that. Apparent weightlessness is pretty easy to achieve. In fact, all of you have felt apparent weightlessness on a good amusement park ride for a split second or two. You felt apparent weightlessness when you've jumped off of a diving board while you're in free fall. You felt apparent weightlessness when you're jumping on a trampoline while you're in free fall. It's one of the reasons we like those things. For short stints. For long stints, it means that astronauts experience continuously, until they get used to it, the physiological feeling of falling, the stomach feeling of falling. So they train the astronauts to get used to weightlessness. What NASA does is it has a 747, a jet, and it flies up high and then it dives down. It can dive down for about 35 seconds. And while it's diving down in free fall, there's no normal force. And so you have about 35 seconds of weightlessness. And because you're in an enclosed room, you don't feel any air rushing on your face or going by your ears. You feel like you're in outer space. And then when it gets down, it pulls back up again. And you feel a much increased normal force because now you're accelerating up. You get pressed down to the floor really, really heavy. And then it dives down again, and you feel weightlessness again. Anybody know the nickname of that NASA jet? Sebastian. It's called the Vomit Comet. Why is it called that? Point number 3. It means that astronauts experience continuously, until they get used to it, the physiological feeling of falling. Until your stomach gets used to it, you're going to be throwing up. And throwing up in 0G is spectacular. And then when the plane pulls up, whoom, right? Well, no, plastic bags. That's why the movie Apollo 13, if you ever have seen that, that's how they did all of the weightless scenes. And that's why if you watch it, not a single scene in the space capsules between Tom Hanks and his astronauts lasts for longer than 32 seconds before there's a camera cut. But Ron Howard tried, because he's the director, he tried to book the space shuttle. NASA wouldn't let him have it, but he wanted to book and film it on the space shuttle. He said, well, we can do that. They wouldn't. So this was the next best thing. And it works. So all that weightlessness was not special effects. They really did it. Good stuff. Example 4. In a cartoon, a character kicks the football the wrong way, but the football orbits the Earth and still goes through the uprights. At what speed was the football moving? If you wanted to orbit the Earth, on the Earth's surface, or you know what, let's say this, on the height of Mount Everest plus 100 meters, that would help you clear everything, any mountains, any trees. So let's go 100 meters higher than Mount Everest. how fast would you need to go? A, are we in orbit? Then I'm going to write gravity is what's pulling me in a circle. I'm going to write big G, big M, little m over r squared equals, don't forget the little m. Oh, what do you ask me to find in A? V squared over r. By the way, you could just go to the previous page and look at the box. Don't. I want you to learn this procedure. Don't memorize that. Know that you can always fall back on Fg equals Fc and just cross multiply your little hearts out. The mass cancels, yes. One of the r's cancels. And I end up again with orbital speed being the square root of big G, big M over r. The square root of 6.67 times 10 to the negative 11. Mass of the Earth was 5.98 times 10 to the 24th. Make sure you are aware of what planet we're talking about. In your homework on your test, sometimes just for kicks, we'll orbit the moon or we'll orbit Mars or we'll orbit the planet Duick or whatever. Make sure you don't always assume that that's the same mass. Divided by. Now, technically, I should write the radius of the Earth plus Mount Everest plus 100 meters. But the radius of the Earth is so big compared to Mount Everest and 100 meters, I'm going to ignore that because the Mount Everest and 100 meters don't start showing up until the 6th or 7th sig fig. Who cares? So we're just going to use 6.38 times 10 to the 6th. Squared? Oh, no, one of the r's canceled, no longer squared. Again, there's a good chance for you to practice with your calculators. I'm trying to remember, I think you get an answer right around 8,000-ish, try. I think just below, if I recall. And again, don't square it at the beginning. I recommend multiplying everything, dividing, enter, and then square your answer. What'd you get? 7,900? 79 what? 7906? Yes. 7.9 times 10 to the 3rd meters per second. See if you can get that. It's just below 8,000, about 8,000 meters a second. We can get that fast, by the way. The space shuttle would usually hit about 12,000 meters a second. All right. If you're going that fast, I'm kind of curious. B, what would a round trip once around the world take you? So what's B asking us to find, Sebastian? Marshall? Period. Are we moving in a circle? What's pulling us in a circle? Let's start out with our fallback of gravity equals centripetal force. And big G, big M, little m over r squared equals little m. Oh, which equation do I want to use for acceleration now? 4 pi squared r over t squared. A mass cancels. Does an r cancel? No, in fact, if you move the r squared up, you can see we're going to get an r cubed kicking around here. If I want to get the t by itself, I think I'm going to end up with t squared equals 4 pi squared r cubed over big G, big M. Oh, are you saying that I didn't need to write the t squared, that I could have gone straight to this? I like that. The joys of being able to cross-multiply. I had a kid who tried to memorize all these variations one year, and this was the unit where she caved. Just can't do it. Yeah, I know. I'm teaching you how to do the math. Memorize Fg equals Fc. Oh, and by the way, it's got 2 Fs. You really only have to memorize 3 different... Anyway. And I like to think it's fairly obvious. Let's plug in numbers. Ready? The period is going to be, you may notice I'm drawing huge square roots because most of these are long numbers with scientific notation, so just, 4 pi squared. R is the radius of the Earth, which is 6.38 times 10 to the 6th cubed, all divided by big G is Newton's gravitational constant, 6.67 times 10 to the negative 11. Mass of the Earth is 5.98 times 10 to the 24th. How long would it take you to get once around the planet? What'd you get? Zach, what'd you get? It's about right, I think. It's in the 5,000s. Five, what? 5069? So let's go 5.07 times 10 to the 3rd seconds. Zach, you got that on your calculator still? Divide by 60 to change it to minutes. Divide by 60 again to change it to hours. How many hours to get around the planet if you could travel at this speed? 1.4, about an hour and a half. And so we go on a bit of a rant about planes right now. You realize right now, to get from Europe to the east coast of North America, it takes you longer now than it did 10 years ago. What did we have 10 years ago that we don't have now? A jet? Which jet? Begins with the letter C. A very advanced jet. It's called the Concorde. It was the only jet that traveled well above the speed of sound. It was built jointly by Britain and France. And it did fly between London and Paris, but that's a pretty short jaunt anyways, so it's really, you don't get the benefits. But it flew between Paris and New York. It did it in about 4.5 hours, very fast. And they did also want to fly from New York to LA. They thought that would be a great flight, or from Washington, D.C. to LA. That would be a great flight. Except because it wasn't built by the U.S., the U.S. got snooty, and they said, you can't fly supersonic above our country. Despite the fact that the U.S. fighter jets do it all the time, you guys can't. So you would have been able to fly from New York to L.A. in about 4 hours. You think that would have sold out? You think any sports team would have chartered that and used that to get from? It would have been a huge success. But they made them fly slowly at about, I think at about 2/3 speed, which meant it cost way more fuel because it was designed to be at its most efficient, at its maximum speed, burned way more fuel, and you weren't getting the benefits. Why would I pay 3 times more to go on this jet when I can pay 1/3 as much and only get there an hour later? So the Concorde company went under about, 8 years ago? 6 years ago was the final flight. One did come here. I went to the Abbotsford Air Show in the late 80s, and the Concorde jet was there. It's a spectacular-looking jet. So what are they talking about now, then? Because, Zach, they're interested by that 1.4 hours. They're trying to see if there's a way we can go hypersonic. And what they're talking about is jets that would go into low Earth orbit and then end up at their destination. So they're saying, hey, could we fly from New York to Sydney, Australia in 4 hours? That'd be nice. You could probably sell it out. You wouldn't be flying 5 or 10 flights a day. But if you're flying 1 a day or 3 or 4 a week, you could probably sell them out. Who knows? Maybe in your lifetime. Because of this. Low period. Hey, don't turn the page yet. C. I wrote, this is all theoretical. Why is it not possible to orbit the Earth's surface in this manner, but it's perfectly possible on the moon? It's all right in here. You could do this on the moon very, very easily. In fact, on the moon, we could put a satellite 10 meters higher than their highest mountain, and it would stay up there just fine. Why wouldn't that work here on the Earth? What's the difference between the Earth and the moon at low altitudes? Show. Air resistance, big time. The reason the International Space Station orbits where it does, it's the orbiting there because it's above almost all of the atmosphere, which means no friction, which means it can stay there. Now, we got to be careful. There are other forces. The sun does exert some gravitational pull, and other planets do. And so any satellite, almost any satellite that we put up there, does have some thrusters and things so that we can tweak the orbit if we need to. But it's minor tweaking. It'll stay up there with no friction for eternity. But yeah, moon, no problem, because no atmosphere. Earth, air resistance would slow that thing down very, very quickly. In fact, it would probably get frying hot traveling that fast, just from the air friction. Now you can turn the page. If it takes a satellite 300 minutes to orbit the Earth, how high is it above the Earth? So you're the CIA. It's time for you to put up another spy satellite, and you want it to circle the Earth every 5 hours, 300 minutes. Oh, let's cross out 300 minutes, by the way. They're not going to get me to fall for that. How many seconds is 300 minutes, please? 18,000 seconds. Okay. 5 hours. So you want to orbit the Earth every 5 hours to spy? How high should it be? Well, what path is this satellite tracing out? A circle? What force is pulling it in a circle? Hey, what do you think I'm going to start out to write out first to solve this question? Big G, big M, little m over r squared equals little m. Am I going to use v squared over r, or am I going to use 4 pi squared r over t squared? Did they give me a velocity or the period? So am I going to use v squared over r, or am I going to use 4 pi squared r over t squared? 4 pi squared r over t squared. Check. Does it matter how big the satellite is once it's up there? Nope. It's expensive to get it up there, but not once it's up there. Anything else cancel? No. Kids are tempted to cancel out an r. It doesn't. And what are they asking us to find? I don't see a distance. I don't see a d in that equation. What are they asking me to find? Radius. Let's get the r by itself. This is going to be a little bit weird. I think when I move the r squared up to the top, I get an r cubed, yes. And I think this t squared can move donk to there, and this 4 pi squared can move donk to there. In fact, I think I get this. R cubed equals big G, big M, t squared all over 4 pi squared, yes? All right, smarty peoples. How do I get rid of a cubed? Ah, we got to find where our cube root button is on our calculator. Who knew that that was actually useful in real life? I mean, I knew it was there, but this is the first time I actually had to use it. This is kind of cool. It's going to be the cube root of 6.67 times 10 to the negative 11. Mass of the Earth. Period. 18,000 seconds squared divided by 4 pi squared. Now, some of you aren't sure where your cube root button is. This is your chance to call me over and I'll help you find it. So you get 14848 and the reason I wrote all of that down is because I'm not done. What this has given me, if there's my satellite and there's the Earth, it's given me that distance there. It's not what the question asked for. What did the question ask for? How high above the Earth? It didn't ask for a radius. The question wants that distance there. That's the height. So how can I calculate the height? It's going to be the orbital radius minus the radius of the Earth. The actual height is going to be 148,48095.9. Your answer button. Minus 6.38 times 10 to the 6th. What height is that? Heck, I can type that in. 148,48095.9 minus 6.38, scientific notation button, 6th. You get 8.47 times 10 to the 1, 2, 3, 4, 5, 6. That's its altitude. Cool. How fast is it moving? Okay. You know how I'm going to start this one? Take a guess. Well, it's gravity's pulling it in a circle. Big G, big M, little m over r squared equals, and I think since they're talking about orbital velocity, by the way, I got to be proper here. Cross out velocity and replace it with speed, because remember, the velocity is technically is supposed to have a direction, but the direction always is changing in a circle, because your velocity is always 90 degrees to the circle, so what we're always calculating is the speed. If I say the direction, tangent to the radius, but wherever the radius is, I don't know. Hey! Oh! Oh, in fact, we've seen this one before. I think we end up with orbital speed being the square root of big G, big M over R. And again, you're going to use R, not altitude, the orbital radius, the 148,480,959, that one. It's going to be square root of 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th, 148,48095.9. Cole, what'd you say you got? Oh, I thought you said you had an answer. My bad. I thought you were interested in learning and practicing and learning from your mistakes. I'll never make that mistake again. The things I put up with. One 4848095.9 square root. You get 5,182.9, 5,180? So, Dylan, here's the question. Is this satellite moving? Yes or no? Yes. Does it have mass? Yes or no? Does it have kinetic energy then? Yes or no? In fact, a fair bit of kinetic energy. A half mv squared, where this v is pretty big. Where'd that kinetic energy come from? Where'd it come from? Not from gravity. Graydon? Where'd the kinetic energy come from? This is one more reason why it's so honking expensive to launch satellites up there. It came from the rocket fuel of whatever ship brought it up, whatever ship brought it up there, had to have enough rocket fuel to, first of all, increase its potential energy by that height, which is a huge height, increase its own kinetic energy to this speed, because it's got to get into orbit to launch something else in orbit, and increase whatever it's carrying's kinetic energy to this speed, and then drop down. Dylan, same question again. Are you ready? Does it have a speed? Does it have mass? Does it have kinetic energy? We have done a lousy job of cleaning up after ourselves. Right now, outer space is littered with space junk, all of which has mass and a huge velocity, 5,000 plus, which means it has a huge kinetic energy, which means if they hit other things, they'll do damage. A real issue right now for the space station is collisions with man-made objects. Even a fleck of paint, if you crunch the numbers for the kinetic energy that it has, it's like shooting a rifle at the space station, which is not what it was really designed for. And so one of the big issues for the next 20 years or so, in fact, I think DARPA is sponsoring a challenge, or it might be one of those X prizes, is can you come up with a cheap, economical way to do what we always seem to have to do, to learn to clean up after ourselves. We've littered the planet. Yes, we've even littered outer space. NORAD, the U.S. military, keeps track of, I think it's around 40,000 pieces of space debris, but it can't track stuff much smaller than a basketball. About 4 years ago, 2 satellites collided and shattered, sending out millions of pieces, small pieces. Paint flecks are out there. Screwdrivers, astronauts' tools. There is at least one astronaut glove floating out there. Google and you can find out the story of how the guy survived and go, holy smokes. Anyways, there's an astronaut glove floating around out there. There is space debris.
Could that fleck of paint kill the astronaut who's on the moon and hit him?
If they were both traveling at the same speed because it's a relative velocity issue, no. But if that fleck of paint is not in a stable orbit, it's slowly going to decay and decay and decay. Now, eventually, it'll probably hit the Earth's atmosphere and burn up. But while it's decaying, its orbital speed is different from whatever orbital radius that it's in at that moment. Those objects will have different speeds. Not good. Not good. In fact, probably in your lifetime is going to be the first situation of us losing a major satellite because it collided with garbage that we didn't clean up after ourselves. I don't know if it's happened yet, but it's getting messy up there.
Do we have anything to defend against what the bigger piece of an asteroid coming toward there?
Nope. The question was, do we have anything to defend against if a big asteroid is coming towards the Earth? Nope. And we know from fossil records it happens fairly often, and we're due. So gather ye rosebuds while ye may. Yeah. In fact, just about 2 weeks ago, NASA revised. They were keeping an eye on one that they said had a 90% chance of coming within, I think it's 100,000 miles of the Earth, which we consider a near miss. And they just, because it's so far away, you all think like Star Trek, we have these great sensors. We really don't. It was far enough away, they revised it. It's not going to come anywhere close to us. But really, we wouldn't pick one up until it was a few months away at best, probably. And probably not much we could do about it, despite what the movies may have taught you.
I was hoping
No,
to
it
have
can't fall
some.
back. It can't fall back up there.
Shoot.
Let's do it. If you can make an electric car out of electric fuel, do you make the rest as well?
Could you make a, sorry?
Like an electric rocket, like the way cars are.
Could you make an electric rocket? Yes and no. We are working on electric airplanes. That would be nice. Okay, we're trying to, probably not a passenger jet, although perhaps, and the envision would be when it lands, you just swap out the battery bank with a new battery bank rather than refuel, and that way those batteries can take their time to charge. There is an electric flying airplane. I think it's a kit plane. About a year and a half ago, a company in Sweden produced it, and it does okay. It's got a range of a few hours. It's very, very efficient. The issue with outer space is to travel in outer space, it has to be a Newton's third law issue. We have to exert a force against the ship, and therefore then exert a force in the opposite. It's got to be some kind of a rocket system. We can't use propellers and things. So we could do a thing like an ion engine where we were sending out a stream of electrons, and electrons have mass, and since those electrons were traveling backwards, momentum is conserved, some momentum would be going forwards too, and since it's force times change in time, and force means mass times acceleration, there would be a slow acceleration. That might work. Japan is trying to build a space sail, so the photons from the sun, when they hit something, do exert a small pressure. They're trying to build a sail about the size of a football field that you could unfurl out in outer space. This has been talked about for about 70 years, but they're trying to do it finally. That you could unfurl in outer space, and the pressure of the light hitting it from the sun would cause it to slowly accelerate. But theoretically, just like the wind is free, you could then sail away from the sun. The big issue is, how do you get something the size of a football field up there? Especially since I've just told you how expensive $10,000 a pound and things.
Space elevator, right?
Space elevator is one they're looking at as well. That would dramatically make it cheaper. Speaking of, we just said the equation for the period was, what did we say it was? 4 pi squared r cubed over big G, square root of Shashan, should you memorize this equation? Nope. Start out with Fg equals Fc, and you can find what you need to. Now, we have a certain type of satellite called a geosynchronous satellite. A geosynchronous satellite is a satellite that stays above the same place at all times, which means if it stays above the same place at all times, you actually know its period. If you want it to stay above the same location on the Earth, what does its period have to be exactly? More specific. 24 hours times 60 seconds times 60 minutes, whatever that is. Your space elevator would be suspended from a geosynchronous satellite, and I can tell you that that geosynchronous satellite would have to be orbiting with a period of exactly how many hours? 24 hours. Now, if you look back at my radius equation here, where we said that the radius was the cube root of this, if you have the same period of 24 hours, are they orbiting around the same mass of the planet? Yeah. Is G the same for all of them? Yeah. Is 4 the same for all of them? Is pi the same for all of them? Any satellite that orbits in a geosynchronous orbit has to be at the same height. All satellites that are geosynchronous are all at the same height. All of the GPS satellites are geosynchronous. There's 64 of them, I think. 60 of them, I think. Europe is launching its own second-generation GPS system in the next decade or so. It's supposed to be going to be accurate to within a few feet. Those will all be geosynchronous. Your space elevator would be geosynchronous. It's very useful to have a geosynchronous satellite. Emily, it's very useful to have a satellite that's above the same place. Communication satellites, we kind of like those to be above the same place so we know where to aim our satellite dish to bounce it off, and then down below on the Earth, on the other side of the Earth. It's very useful for them to be in the same location. But since they all got to be at the same altitude, it's getting crowded. It's getting crowded. Now, thankfully, it's a three-dimensional altitude that they can, in all directions, but it's getting crowded. Example 6. I'm going to skip example 6, and instead I'm going to assign homework. I think you're getting the hang of this. Homework, you can try. Here's what I assigned my block A's. 2, 3, 4, 6, 7, 9, 10. 2, 3, 4, 6, 7, 9, 10. Let me circle that, and then I got a short video to show you. Can you wait? There's like 5 minutes left.